So we've been talking about experiments in the last lesson, and we talked about the four components of an experiment, which are what are the four main components of an experiment? Without trying to look. Not quite. Close with that word. Random assignment. I heard. Control. Another one that begins with C. Comparison. And another one that begins with R. It's CCRR. No, we already did random. Not repetition. It's close. Replication. Okay. All right. And why do we do random assignment? Because we want our groups to be as roughly similar as possible. Okay? Because if there's too much variation in the groups, we won't be able to tell if a treatment works or doesn't work. Okay, so we want to account for that variation. Now, sometimes there's a couple of different types of experiments that they're both random, okay? But there's slightly different types of experiments rather than just a random experiment. Yesterday we talked about completely randomized. But sometimes your situation may be set up where you might use one of these two. And the first one is called block. Okay? In other words, a blocked random experiment, which is kind of like stratified when we talked about sampling, random sampling. So remember, we got the Jennifer John study. Okay? Everything was identical on their resumes except for the names. It was sent to 127 science faculty lab members who rated the applicant's hireability and estimated their starting salary. Okay? So imagine the experimenters got 8 faculty to evaluate. We're just going to keep the numbers simple. 4 for John, 4 for Jennifer. And then you see the hireability ratings. So based on this, so these 4 faculty members had John, and those are the favorability ratings they gave him. And then the same with Jennifer below. Does there seem to be a substantial evidence of hiring bias? No, I mean, John is favored, but there's some overlap here. Like we've got some overlap here. And really, there's one situation where John's given a high one and Jennifer's giving a low one. So it's not huge, right? So because of the overlap, there is just a small advantage for John. And that could be due just because of the variability in the this faculty members, you know, not because of hiring discrimination or not because of hiring bias. So there's just a small, so we would say no real evidence of hiring bias or discrimination. What if we look at the 8 in a different way? In that 4 of them were from Tier 1 universities. Of the 8, 4 were from Tier 1 universities. 4 were from tier 2, with tier 1 being more prestigious, okay, than tier 2. And these are the results they got. So notice the purple ones, those are faculty members from tier 1 universities. And the orange X's are faculty members from tier 2 universities. So if you compare the purples and if you compare the oranges, do you see more evidence of hiring bias? Yes, because here it looks like, yeah, there's a significant difference. And same with here, like there's some overlap here, but there seems to be more of a significant difference. Okay. So what happened is we blocked these faculty lab members by the university they're at, right? So because they fit into two groups that were pretty different from another, much like stratified sampling, where we split them into groups and the groups are different in some way from each other. Well, these two groups, these two blocks are different because one has a set of faculty members that are at a more prestigious university. Okay. So we would say, broken down by tier, which we would call, sorry, broken down by tier, which we would call the block, the blocks, there seems to be much more evidence of hiring discrimination. So something you may want to consider when you're designing an experiment that could give you more reliable results would be blocking if you can. You know, like if you say are going to do some kind of experiment on people, maybe you might want to block by male and female. Maybe you want to have a certain number of males and females in each group. One in the treatment group and one in the control group, okay? Because maybe there's a difference into what you're experimenting with between men and women. Maybe there could be a difference between children and adults. Maybe there could be a difference between, like I said, you're doing senior school, between grade levels. So maybe you want to do 4 blocks and make sure that in your treatment group, you have grade 9s, 10s, 11s, and 12s. And in your control group, you have grade 9s, 10s, 11s, and 12s. That's blocking. It's like I said, it's like stratified random sampling, but we only use the word stratified when we sample. We use blocking when it's an experiment. Okay, so if we want to compare within school tiers, we need to implement what's called a randomized block design. So in this randomized block design, they are the experimental units, which in this case would have been the faculty members. They're grouped by some similar trait. In this case, their similar trait would be the university they belong to. Then you take units from each block and put them into the 2 treatment groups. Or sorry, one into the treatment group and another into a control group if you have 2 groups. What's that? What I wrote? Grouped. Okay. So it's the stratified sample of experiments. But we don't really use stratified when we talk about experiments. We use blocking. We use stratified when we talk about surveys. But there is a comparison between the two. So what it does is it reduces variation between the treatment groups at the start of experiments and makes it easier to show that the differences in responses are really due to the treatments. Rather than chance variation in randomly assigning them. Okay? Because what we want to do is we want to try and control for everything we can in an experiment except the treatment. Right? Because we want to see if the treatment itself is going to make the difference. If it does, then we can talk about cause and effect, which we'll talk about a little bit later on. Okay? If it doesn't, well, then we have our answer too. So here's sort of a visual way of how we block it, and you could be asked to describe a randomized block design. Much like in the previous lesson, you were asked to describe a completely randomized design of an experiment. So here we've got, this is a slightly different example. We're not using 4 and 4, we're using 6 and 6. So you got 6 professors or 6 faculty lab members from tier 1. 3 go to John, 3 go to Jennifer, randomly. Same thing with tier 2. 3 go to John, 3 go to Jennifer, randomly. So then you've got your group from tier 1 and tier 2 mixed up. So we want to compare the hireability within each block. So I want to look at within tier 1 what's happening. And then I want to look at within tier 2 what's happening. Is one getting favored over the other? Is John getting favored over Jennifer, or perhaps the reverse? Who knows? Okay. And then I want to compare, sort of combine the results and compare them, right? So we want to, so basically, when we do all this, we're going to get like a couple of different things, right? We're going to get the combined results like we did here. And then we're going to get it broken down by tiers like we did here. Okay. So to do this, and there's not a lot of writing involved here, okay? But we want to basically say the addition with the block design is we want to say at some point in our description that we are going to block by tier, okay? So I'm going to start right off of that. Block the science faculty members. By a tier. So if it's the above example, I'm going to have 6 in tier 1 and 6 in tier 2. Okay. But the groups I'm going to make are going to have the treatment group and the control group are going to have a mix of tier 1 and tier 2. So in each block, assign a faculty member from 1 to 6. Or assign a faculty member a member from 1 to 6. Of tier 1. Randomly assign 3 to the treatment group. Which would be, so to the treatment group, which could be John. and the other 3 to Jennifer.
The Jennifer group would be the control.
Sorry, I won't even, I'm going to just call it to the John group, to the treatment. They're both treatment groups in this case. Yeah. One's not, yeah, there's no control group here in this situation. And then do the same with the tier 2 group. So we're going to have 6 in the John group. By the time this is done, we're going to have 6 in the John group and 6 in the Jennifer group. Then have the members rate the applicants or the applications. Compare the results in 2 groups. The Jennifer John group, where Jennifer is made up of 3 tier 1 and 3 tier 2. John is made up of 3 tier 1 and 3 tier 2. So compare those 2, the Jennifer John groups, the John Jennifer groups. Get the overall. And then do within each block. And within each block. So then take those higher ability ratings and then sort of rearrange the groups so that, okay, now we're going to have all the tier 1s. How did they rate? Okay, what's the difference there? Was there a more rating for John than Jennifer? What did it happen in the other block as well? Okay. Okay, so that's randomized block. Another way you could do it, and this sometimes students get confused between these 2, is something called a matched pair design. Okay. It's a type of randomized block, okay, which each block is, oh, I have the wrong thing. Each block is composed of 2 similar units, 2s. So they're put off in pairs. That's why we call it matched pairs. Okay. Sometimes the matched pairs is the same experimental unit receiving both treatments. Okay. But the order of the treatments is randomized. So before I go on to this depression study, let me give you another example. Let's say we want to see, does music help students study better? Okay. So what I may want to do, or sorry, does music help students study better in this AP Stats class? So what I would want to do is I could do it, I could match one of 2 ways. I could take all your marks and say, okay, I'm going to take the top 2 students in the class, and one's going to get music and the other one's not. And I'm going to randomly decide which one gets. Then I'm going to take the second 2 and do the same. Second 2 and do the same all the way down. That's a match pairs because I'm pairing everybody off, right? And then I'm doing comparisons between those, and then I'll get a general comparison. Or, just a second, I could pair each of you off with yourself. In other words, take each one of you and say, flip a coin and say, heads, you're going to do, you're going to study without music first, and tails, you're going to study with music first. And then you're going to do the opposite after. So each one of you are sort of going against yourself. You're being compared against yourself. Those are two types of matched pairs. Okay? To recognize matched pairs, just look for the word pairing off, or the phrase pairing off. That's really how you can do it. Okay? Blocks are bigger. Pairs are obviously smaller. So let's look at another example. So in this study, researchers wanted to test if taking a fake pill, placebo, would actually alleviate depression symptoms, even though the pill had no active ingredients. 35 people enrolled in the study, all had major depression, none were taking any medications. Because depression varies greatly between individuals, the researchers implemented a matched pairs design. Well, you could do this one of two ways. Okay. You could take pairs of people who you consider, I guess, the most depressed. And then after that, like if you rank them according to depression, you could do that. Maybe that's not the greatest though. What might be better? What might be, how would you pair off? Would you pair two people off, or would you pair off yourself? Pair off yourself and maybe have a time where you receive the fake pill and the other time when you don't receive the fake pill. I think, is that what you would do? No, there's no other pill. Yeah. So you could, okay, so you could like flip a coin and say, okay, you're going to take the fake pill for a month. And then you're going to be off that pill for a month. What's going to happen? And then flip a coin again. Okay, first month, you're not going to be on any medication. Second month, you're going to be on a fake pill, even though they don't know it's a fake pill.
As of their life before they end, or is that absurd?
Yeah, they could do that.
Like they couldn't say, I feel better now.
Well, I guess if they got information from them that allowed them to make that determination, right? I mean, all had major depression, none were taking it. So it's kind of hard to tell, right? How was this diagnosed, right? I mean, was there an interview, or was there just some questions where a depression scale was made out of that? Who knows? But yes, you could. Yeah. You're paired off, okay. You're either pairing off individuals and assigning treatment to one and alternate treatment or no treatment to the other, or you're pairing off somebody against themselves. There's two different types of matched pairs. Okay, let me write this. Let me describe this, and maybe this might help. Okay. So for each subject, we're going to do. You guys said compare among yourself. Good idea. For each subject, flip a coin. Heads indicates big yes. A fake pill for a period of time. And then no pill. Oh, that disappeared. It's
But if they compare it to their the experiment solves, because that was your math.
Sorry, say again.
You couldn't compare it to the only experimental cells, because that would be your math here. Because they would all have,
Depression.
they would all have their
No medication.
no medication.
Right. Yeah, good point. So heads indicates they get a fake pill for a period of time and then no pill for the same period. So say at the end of each period, depression level is assessed. And that could be through a questionnaire, a professional interviewing, maybe a PET scan. Depression level is assessed. And then compare measurements for each subject. That would be a match pairs. So you're pairing individuals off and then pairing a whole list of individuals off or pairing individuals off against themselves. Okay.
For two people. Do this for two people.
Yeah, it would have to be, you'd have to be very, that's why we wrote this one, because it's better, I think. Okay, it's possible to do it with two people, but would your results be accurate?
But in general, in a math pairs like experiment, if you were to do it with two people, would you be comparing it across the people and then across the groups? You know what I mean? Or would it?
Well, yeah, I mean, you could do both. It's possible to do both to get more information. I don't know if you get more information out of it, but it's possible.
Like started for example, doing things for kids to get some look at tests, get the eliminate, switch back.
Right. So let's say for a month, they get the,
Have like people who test for free pill and then people who do like then make it in a place not doing the fake pill.
okay, now that you're creeping into another area, which is good, because what happens, this sort of speaks to, should people know what they're getting or should they not know what they're getting? Should the experimenters know what they're giving? That's the placebo effect, right? That means like, I wanted to, I should have done it like, I should have done it like the second test. I should have just brought in a piece of generic candy and just said to you guys, okay, this is a smart pill. And I want each one of you to take it before you write the test. Okay? It would not be surprising if students did better, because it's something in the brain that's saying, well, if I'm doing this, it's got to be better. So maybe it's a result of greater confidence. Who knows? Right? But it can happen. You know, like you burn somebody and say, well, here's a nice treatment for you. Okay, this treatment I think really worked, and it's nothing. It's like cream. But people will report. They'll say, yeah, it feels better. Because it is. Yes. Sorry.
What was the point of flipping the coin? Like, what happens if you don't get meds?
Well, because then you're making a judgment as to who goes to which one.
But, I mean, what do the people who got pills go into no pill at all?
Yeah. No, well, no, hang on. Every person. Okay, imagine 2 months. You step up, I flip a coin and I say, okay, heads, you're going to take a pill for 4 weeks, and then you're going to take nothing for 4 weeks. So then I flip. So the groups themselves could be unequal. Tails would mean that you do the opposite.
So
You don't take the pill for the first month, and then you take the pill. Yeah. Good question. So what happened as a result here? On average, participants reported less severe depressive symptoms after their week with the fake pill. It said week in here. I changed it to month because, I mean, medication usually takes longer than a week. On average, participants showed increased new opioid receptor brain activity in regions of the brain associated with emotion and stress regulation. Basically, they believed in this pill and it caused some kind of biochemical change where they felt better. And fake pills have been used for these things. And these fake pills have a certain name. They're called placebos. Where it's like, it's just, there's no active ingredient in it. That's the placebo. Okay, so that's the placebo effect. There's a difference between placebo. Placebo is the actual. Which is the placebo effect. Yes. What? You faded off on me. That's what? That's psych? Yes. But it's also statistics too. Because a lot of what you do in psych is you do studies. Because you want to see, like, do certain treatments work? Do other treatments not work? What's going on? Or if somebody comes up with this big study and says, hey, you know what? Bananas significantly reduce depression. And then they're going to explain their whole process of how they did it. Well, you, as a statistician, not just a psychiatrist, need to be able to look at that methodology and say, you know what? That's flawed. There you go, bananas. Okay, maybe I'll do that. Maybe I'll do that next year with the group. Is instead of a special smart pill, I'll just say, you know what? Bananas help you perform better on tests. Here, take a banana before you write this test. No, I want to give them an actual math test. Anyway. Yes, they really do. Yeah, a lot of times it's called a sugar pill because it's got no active ingredient in it.
Like at the end of each year, you have like subjects who have done like first month, second month. And you have their interview questions from the first period and to the second.
Yeah.
How are you comparing?
Well, obviously they must, if you're using a questionnaire, usually with a questionnaire, you're getting the depression rating. So obviously they're comparing the depression rating with the fake pill and without the fake pill. So maybe the depression, I don't know, let's just assume for argument's sake, the depression rating is out of 20, with 20 being the most depressed and 1 being the least. So maybe in the first month, they get a 14.
Yeah.
And then in the second month, they get an 8. Right?
Yeah.
That's how.
But what is the purpose of the match here then?
Because you're trying to prove that the treatment works.
But couldn't you just like ask them when you're coming to the experiment, what is your depression rating, and then have them just help, and then ask them.
Right. But in the very first lesson, we talked about something when you ask people. Sometimes people have a tendency to exaggerate. Hey, I feel okay. I'm okay. I don't want to tell anybody I'm depressed, so I'm just going to say I'm okay. Right? Wouldn't most people do that? So that's why you want to measure before and after. Okay. So a placebo, inactive treatment. Sugar pill, salt water, IV drip. Okay. The placebo effect is when the subject's belief of receiving an active treatment leads to some measured response, even though the treatment is actually inactive. Chocolate milk reduces concussions. Just remember that. I'm just putting that out there. Bananas improve driving ability. So let's just do random ones of these. What else? Give me another one. Give me another something that causes some. Anyway, another one.
Doesn't pineapple juice like speed up your recovery? Yes, it does.
Pineapple juice speeds up
Amazing.
recovery. Sure. Oh, recovery. Okay. Interesting.
I'm gonna try to buy it.
Okay. So how do we get around these things? How do we got to be careful with these things to sort of reduce the placebo effect? Is we do blind studies. A single blind study, one of the groups, neither the subjects nor the researchers or the experimenters are aware of who's getting the placebo. One of the groups is not. Usually it would be the subjects that wouldn't know. But there can be bias if the researchers know which one they're giving. Because why? Because maybe a researcher has spent 10 years on developing some special pill and wants a good result, right? Let me just finish this. And so in a double-blind study, both the subjects and the researchers are unaware. No, it's not. This is one or the other. This means one or the other. Single blind means one or the other doesn't know what's going on. The subjects or the researchers.
Why do the researchers not know what the subjects do?
I just explained it. I just said it.
I mean, like, based on the result, like, if you gave someone a placebo effect, and I think, like, it doesn't matter the bias. If someone knew they were getting a placebo effect, then they would report the same results. They did that.
Say that again. No, hang on. Say that again.
Like the subject.
Yeah.
You gave someone a placebo.
And they don't know it's a placebo. And they do know it's a placebo. Now you're going to fight the placebo effect, which is going to affect your results. So that's not good.
Yeah, so how come they would know it's a placebo, but the researchers wouldn't? It's just gonna, so people don't really do.
Maybe it's a bad accident. Like sometimes it just happens. Like chocolate milk reduces concussions. Okay. And you just tell somebody like, okay, you guys are gonna have chocolate milk, and you know you find a group of people that have concussion-like symptoms or something like that, or concussion. Let's say chocolate milk helps you recover more quickly from concussions. So you have a group of people that have suffered concussions in the last whatever. You say, okay, you randomly split the groups. You see, you guys are going to receive chocolate milk. We're going to measure how your symptoms after a certain 2 weeks. You guys are going to receive nothing. Yes.
So it's just because this one's like a placebo pill and this.
Right. Yeah, I mean, you're right. Ideally, you would always not, if it involves a placebo, you would always not want the subjects for it to be a good experiment.
The sentence there reads, in a single blind.
Oh my God, are you kidding me?
Nor the researchers are unaware. That means that both the subjects and the researchers are aware. I just want to confirm that that sentence is incorrect.
That's the big loss.
Yeah, thank you. It says neither the subjects.
Yeah, I can read. I can read.
So that means that you're both aware, right?
Neither, yeah, it's like neither are unaware.
I think you should say either the subjects or the researchers.
Okay, we got an English lesson going on here.
I didn't even need one of these lists either. Either the subject or the research. Yeah.
Feel better?
That's either the subject or nothing. Neither the subject or sports both. Either. This one. Okay. Thank you.
Yes.
I know it's still blind study, so that is word. But I don't think like, this college board, are you going to ask for the definition of trust? With members? Like it's not.
Yeah. So basically, let me finish this. If you blind the subjects, it controls for the placebo effect. If you blind the researchers, it controls for, how would I say it? Controls for influencing the results. Which really is confounding. Because remember, we talk about confounding experiments. Because like I said, you could have somebody who spent years developing some kind of method to help something. And you know that when they start testing it, they want it to work badly. And some want it to work so badly that they're willing to cross certain lines. Okay, so there's ethics along with this as well. All right, finally. What can we do with observational studies and what can we do with experiments? And what can we do when it's random or if it's not? This is called the scope of inference. Remember, inference means conclusion. What kind of conclusions can I make? So, if I randomly select individuals from a population and either do an experiment on them or do some sort of sampling or observational study, I can make an inference about the population. If I do random assignment of individuals to groups, in other words, random assignment in an experiment, now I can make inferences about cause and effect. Okay. So like if I surveyed a sample of senior school students, right, to ask them, how much sleep do you think you get on average every night? Just something like that. Okay. So whatever was, if I do random sampling, I should be able to make a conclusion about the population, the senior school students at BH. Okay. I can't make a conclusion about other populations, but I can't say going to BH causes more sleep or going to BH causes less sleep, even though I'm sure some of you might be convinced of that. Okay. But if I took you guys, senior school students again, made randomly assigned 2 treatment groups, one to receive, and they don't know this, some type of treatment for sleep, to get better sleep, and then the others don't receive any kind of treatment for sleep. And then can I say, does this treatment cause better sleep or worse sleep? Then I can make a conclusion about cause and effect, because I made it into an experiment where I randomly assigned 2 groups. Okay, that's basically what I'm saying. So here, you see there's 4 situations. Subjects were randomly sampled from a population, randomly assigned to groups. That's the idea. That means yes for both. I can make a conclusion about cause and effect, and I can make a conclusion that applies to that population. On the other side, if both were not, well, then it's no and no, and that's the worst one, right? And then we have the mixed ones. If they were randomly sampled from a population, yes, I can make a conclusion about the population, but I can't make a conclusion about cause and effect. Here, they were not randomly selected from a population, but I can make a conclusion about cause and effect. So just as a final sort of little question, here's 4 situations. Which ones do you think they are? Which of the 4? 30 students volunteer for an experiment. Randomly assigned to 2 treatment groups, music and no music, and then test scores are recorded. Not randomly sampled, but randomly assigned. So not randomly sampled, were randomly assigned. Do this one. Random sample of 30 students, randomly assigned to 2 treatment groups. Kind of obvious. Yes and yes. I can make a generalization about the population. I can make an inference about cause and effect. Random sample of 30 music, asked if they listen to music when studying, their scores are recorded.
Random sample, but not random.
Random sample,
But not random.
right. And then this one, we've got 30 volunteers, no random assignment, so that's clearly no and no. Okay. All right.